Okay, in this video, we're going to show that the sum of the first n natural numbers is the same thing as this expression right here, n into n plus 1 divided by 2, where n, of course, is a natural number. Alright? Okay, and we can show this that this is true by method of mathematical induction. Okay, so we're going to use the principle of mathematical induction, which tells us that if we are to prove that it is a propositional function, okay, for example, we can call this a statement P. So the statement can be written as P of n, right? That is a statement depending on n, that this left hand side is something as the right hand side. So you have to show that this is true, otherwise it's just a claim, right? Okay, so to do this, we start off with the base case. The base case means we pick the first element in the set we're considering. Here we're considering the set of natural numbers, and the first element here is 1. Take it to be 1, right? So in that case, we're going to show that for the base case, that is a kind of verification, right? You put in 1, which is the first element, and see if the left hand side will be the same thing as the right hand side. Then after that, we go over to the induction hypothesis, which we have the name mathematical induction. Okay, so first of all, the first thing you write down whenever you have to prove something is to write down proof, right? So this is the name of what you'll be doing. You want to prove, you want to show that the left hand side and the right hand side are the same. So we start off with one of the sides, right? So for the base case, so we say for n equals to 1. So we say for every natural number. So n can pick any of them. So when n becomes the first element, which is 1, alright, what happens for the first case? So you notice that on the left hand side, we have to add 1 to 2 to 3 up to n of them. So when n is 1, it's just the first element, there is no addition there. So you just have 1 on the left hand side. Let's see if the right hand side will also give us 1. Well, we substitute 1 for n on the right hand side, we're going to have, in place of n, we have 1. Then in brackets, we're going to add 1 to this. Then we're going to divide this by 2. We still put 1 for n. So in place of n here, we put 1 and 1. So you notice that when we add these two 1s together, 1 plus 1 is 2. 2 times this 1 is 2. Then we divide 2 by 2. The result is 1. That means that 1 is equal to 1. And that is true. Right? So that is true for the best case. Good. When we are operating best case, so you notice that this is the best case. Yeah. The next step is to get into the induction hypothesis, which consists of 2 parts. So we put down here induction, hypothesis. So let me just write in short, induction. Alright. What we'll be doing here will be, first of all, we'll assume that, okay, since this statement is true, the statement P, okay, is true for the base case n, which is the first natural number, and there are infinitely many natural numbers, right? It's not finite, infinitely many, but countable. Okay, so for any arbitrary natural number, which could be maybe for 8 instead of 1, let's say we want to consider for 8, for 20, for 99, those are natural numbers, right? For an arbitrary natural number, we'll assume that this statement is true. Then we'll use it to prove that it is true for the successor of any arbitrary natural number. So we say, let's assume, that will be the first part. Assume that the statement, so I said let's give the statement a name, let's call it P of n. So we assume that this statement P of n is true for an arbitrary, okay, for an arbitrary natural number, let's say k. So this k is just any natural number, which it can assume the value 22 or whatever natural number, right? So we assume that P of n is true for any this. That is, what that means is that on the left hand side, you're going to add the first k natural numbers. We have 1 plus 2 plus and so on and so forth up to k. That's what it means, alright? Then when we add that, we assume that it is the same thing here. That is, we assume that this statement is true. So that means that the right hand side is assumed to be this, right? We divide it by 2. So we assume that this is true. Then the second part of the induction hypothesis is that we are going to use the fact that this is true, okay, to show that it is true for the successor of k. Now, when we talk about the successor of a natural number, the successor of a natural number is the next natural number. So if we have 2 as a natural number, the successor is 3. 3 as a natural number, the successor is 4. So That means the successor of a number is just that number plus 1, alright? So the successor of k is going to be k plus 1. So that's what we do. In the second part is that we will show that. So we have to show that, or maybe not show that, since we have to prove. We have to show whether, okay, the statement P of n is true for k plus 1. That is the successor of k, where k is any natural number. Good. So let me do it right here. Okay, what that means is that we'll check for k plus 1 on the left hand side. That is, if we are to add k plus 1 natural numbers together, will we get something of this form? Okay, where each of these n's will be replaced by k plus 1. So let's add them. Say add 1 to 2 to 3 and so on and so forth till we get to k plus 1. But take note that before reaching k plus 1, we first of all reach k, right? When we reach k, we now add k plus 1. That's because after 2, the next number is 2 plus 1, which is 3. After 3, the next number will be 3 plus 1, which is 4. So after k, the next number will be k plus 1, which is where we want to stop, right? Now look at this equation. Maybe let me give this equation a name. Let's call it equation 1, because that's the first I want to consider, I want to tap, right? Now notice that when we add 1 to 2 to 3 and so on till k, we call it this, we assume that this is true. So what we'll do is that from 1 to k, since it's the same left hand side and this is equal to that, we will say that, okay, from the assumption, we will say that we replace the first, some of the first k terms with this. That is, we're going to have k into k plus 1 divided by 2 for the first k terms added together, right? Then we now add k plus 1. Good. So to prove that something is true, we need to use one of the sides to show that it implies the other side, right? So if you use the right hand side, you want to show the left hand side is true. But here we're using the left hand side to show that the right hand side is true, using n as k plus 1, which is the successor of the arbitrary natural number k. So the next thing is to try to get something of this form, where each of these n's will be replaced by k plus 1. That's how you know it's true, right? So we add these two fractions together. So when we add these two fractions, notice that we can add fractions easily if they have the same denominator. So what I do here is to multiply the fraction by 1, and they form 2 over 2. So we notice that the denominators are the same. We can easily add the two fractions by keeping one of the denominators, and then we add the numerators. So we keep 2, then we add the numerators. This is k plus 1, k plus 1, so let's take this step by step. We add it with this other part, k plus 1 times 2. Which is 2 times k plus 1. Okay, so you notice that k plus 1 is common in the numerator. We will not rush to multiply everything. We factor out the common factor. So you notice that the common factor in the numerator is k plus 1. So you factor it out. This is it here. When you factor out k plus 1, what will be left will be k here, and then 2 here, that's plus 2 here. That's k plus 2, we divide this by 2. Good. Now notice that we can rewrite this to have this form, where each of these n's will be replaced by k plus 1, and this is how we're going to do it. Okay, so this is going to be, I'm going to put down k plus 1 first. So put down k plus 1, and let's do it this way. We have two brackets, right? This first one is k plus 1, which is this k plus 1. Then I'm going to write this k plus 2 as k plus 1 plus 1, right? There's k plus 1. And then we add 1 to that. Good. And then the denominator stays the same. It's 2. So notice that this part, if we call it n, of course, that's what we did. Say true for k. We have to show that it is true or whether it is true for. So this is n into n plus 1 divided by 2. That's what we have here. And the reason why we're having k plus 1 is because we wanted to show that this statement is true when n is k plus 1. And we've shown that the sum of the first k plus 1 natural numbers can be written on this form, where the n is replaced by k plus 1. That means that the statement is true for all n. So the conclusion is how you conclude. You say, after showing that it is true for the successor of any arbitrary natural number, you say that, therefore, by principle of mathematical induction, that the statement P of n is true for all natural number n. That's it, right? So when you're done proving, you can either say proven or you draw the box and share. Okay, thanks for watching. Please share this video with your friends, and I'll see you in our next video.